Okay, we're going to look now at the binomial theorem, which comes out of the binomial expansion. The binomial theorem. Binomial theorem is one that is derived from the binomial expansion. Now the binomial expansion, so we're talking here about a binomial, which is a two-term polynomial. So a two-term polynomial is x plus 2, so these are all binomials. Okay, y squared plus 4, xy minus 7x. These are all binomials, two-term polynomials. You've done work with trinomials, with quadratic trinomials, such as this, and you factorized, and etc., etc. So that's what a binomial is. Now the binomial theorem comes from the binomial expansion. So let's have a look at what that's all about. Let's take a binomial, let's take a plus b, and look at the expansion of it as it's raised to different powers. Okay, so a plus b to the 0, which is quite a trivial result, a plus b to the power of 1, which is just a plus b, isn't it? It's quite trivial also. A plus b to the 0, anything to the 0 is 1, as you know. A plus b squared. So this is how the binomial theorem is where it comes from is an examination of the expansions of a plus b to different powers. So we just write a few down here. A squared, I think you probably know these ones, just 2ab plus b squared, and that's all good. And if we did a plus b cubed, okay, so we take this and multiply by a plus b, what you'd find is that you had a cubed plus 3a squared b plus 3ab squared plus b cubed. And what we're picking up each time is we've got, look at that, one more term each time, so it's the power 3, we've got 4 terms, power 2 had 3 terms, and so it goes on. And a plus b to the power of 4, now so far we've got these quite quickly, these results. A plus b to the power of 4, now that's all of that. What we do is take that and multiply it by another a plus b and do all this, and you end up with a to the power of 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the power of 4. Okay, now I know a little bit about the binomial theorem, and that's how I was able to come up with that so quickly. You would have to have just done what I just did there with that expansion to come up with that. But let's examine some things now, and that is what I really want to look at are the coefficients of all these terms of the terms. Yeah. So if I go, what I might do is go to a nice bright color here, and just what I'll do is we'll highlight the coefficients. Okay, so we've got ones here, we've got ones here. This is a 2, this is a 1, this is a 1, 3, 3, 1, this is a 1, 4, 6, 4, 1. If we take these and put them into a row by row format and in a triangular format, that 1 comes across there. Out of that row we get a 1, 1. Out of this row we get a 1, 2, 1. Out of this row here we get a 1, 3, 3, 1. And out of this row we get a 1, 4, 6, 4, 1. And we get this triangular sort of, if we rack it up like that, like a sort of like an equilateral triangle, or an acute angle triangle, then what we end up with is what's called Pascal's triangle, and that is what you're looking at, and what it is, what it represents. Pascal being a triangle, being a prolific, famous mathematician. He's credited with discovering Pascal's triangle, and they're all just the coefficients that have come out of those expansions. And why it's so interesting, and what gave the binomial theorem its legs really, and gave it some momentum, was the fascinating patterns that come out of this triangle. So what we can see here is that there's all sorts of things going on. There's all sorts of patterns. Each number, you might have noticed, is made up of the sum of the two numbers immediately above it. So the 4 here is made up of the 3 and the 1. the 3 here is made up of the 1 and the 2, that 4 is made up from there, etc., etc. So we can come up with the next row just by doing those sums. So for us to maybe work out what a plus b to the power of 5 is, rather than do all this times a plus b, we could just go and make another entry into our triangle. So I'm just putting the number here that represents the sum of the two numbers above it. So 4 plus 6 gives me that number, 6 plus 4, 4 plus 1, and then I need to go over a little bit to finish it off. So there's one more entry in each row, and you will notice that they bookended with ones, that the first number in is the same as the power of the expansion, so the first number here in the row, and that it's palindromic, 1, 5, 10, 10, 5, 1 reads the same both ways. It's symmetrical about the middle, so 1, 5, 10, 10, 5, 1, 1, 4, 6, 4, 1, lots of patterns. But for the expansion now, we go, well, I don't need now to work this. I know what the coefficients of this row are. So it's 1. My coefficients are 1, 5, 10, 10, 5, 1. And now I just need to put the algebra in. A to the 5 goes there. A to the 4b goes here. So what you see what's happening is that the powers of my a start at 5 and decrease with each term, and my b power starts at 0 and increases with each term. There's a plus in there. There's a plus in there. So what do we have there? We had a 10, a 5, and a 1. So this one's going to be a squared b cubed, always with those powers adding up to 5. Now it's plus 5 a b to the 4 plus 1 b to the power of 5. There's my expansion. Fantastic. So we can keep going like this, but you know, if we want to do a plus b to the power of 12, well, you know, we're going to have to go 12 rows down, and it's going to take up a lot of space. And this is how the binomial theorem was generated, if you like, with Pascal's triangle being discovered as the coefficients of our expansions, and then it took on a life of its own, just in terms of the magnitude of interesting mathematics around the triangle. And I'm going to show you a few of those now. If we have a look at my coefficients here, 1, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, if we put those into a spreadsheet, like so you can see, I'm just taking, if we took these numbers, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, so all I did here was I created a spreadsheet. See, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And all I've done, if I click on any one of these cells, is every cell is equal just to see, this one's equal to E8, that number there, that cell there, plus D8, which is that one there. So the 35 plus the 35 gives us the 70. The 210 is made up of the 126 plus the 84. So very easy to just write a formula and fill down, and you can create a huge triangle. That's not so interesting, but if we go through and decide we want to colour the, let's say we're colouring all the odd numbers. Okay, this is what it would look like. So we just colour in all the odd numbers. The second one down is an odd. If you go back, that's odd, that's odd, that's odd. So every second one there is odd. Okay, and then we get some little clusters in here that are there's little clusters in here. So we've got a couple of odds there, and then we get a couple of odds in here. So it starts to cluster up a bit. They're the odds. So the odds are coloured. Now, if we zoom in, get lots more information and zoom in, this is what we get. And the odds are coloured there. So we get these massive triangles in the middle full of evens. This is a fascinating, look at this pattern here, a very famous pattern known as Sierpinski's triangle. And that is just looking at and shading shading the odds and leaving the evens white. And look at all so we get these patterns of triangles that get smaller and smaller. And if we look at what's called mod 3, so we look at the patterns as we now start to look at the remainder when we divide by 3, and if the remainder is 1, then they're in blue, I think, and if the remainder is 2, we go with red and we get some more patterns. If we do the same with mod 4 and mod 5, we get more and more pretty patterns, all based around Sierpinski's triangle, and if you like, the patterns that shoot off that. Okay, so back into our binomial expansion, and let's now examine how we're going to find these values. Given that we can keep producing rows, but that's going to be very time consuming. It's better than having to do these full expansions. We have sped the process up, but I still want to know what's a plus b to the power of 12. Okay, so what we discover is that actually these numbers are related to combination mathematics, factorial mathematics, and I'll show you how. So this is row 1 here. This is row 1. This is row 0, and this is row 2. So if we look down, the row number corresponds to the power, and this on these rows we have position 0, 1, 2, 0, 1, 2, 3. So we always end in the number of the power that we've got. The first number is in position 0. So let's go down to say there's 10 here. That is in row 5, position 0, 1, 2, position 2. And what we can do to find the value of that, the coefficient in that position, is calculate 5C2. So if we go in and do that now, I'll just punch that in. It's it's a combination 5, 2, hit enter, and you can see that's 10. So if we want to go and find out what a plus b to the power of 12 is, well, we need to, the coefficients start with 12, 0, which is 12 zeros 1. So anything n0 is equal to 1. That's something we need to know. We start with a to the power of 12. Now our second term will be 12, 1. So 12, 1 is going to be in this position. So the coefficients along the 12th row of Pascal's triangle are going to be 12, 0, 12, 1, 12, 2, 12, 3, 12, 4, all the way to 12, 12. So there are 13 coefficients, 13 terms, and our powers of A reduce and our powers of B increase. So we would get this kind of expansion. It would go on like so. A to the 9, B to the 3. And it would go on like this, and we'd end up with the very last term being 12, 12, B to the power of 12. And that would be our full expansion. We can use the calculator to pull out these values here, and now we can calculate the expansion. We can work out the expansion of any binomial to any power using our knowledge of NCR. So let's just pick out another couple of things here. So n0 is equal to 1, and in fact nn is equal to 1, because n0 represents our first number in our Pascal's row, and nn represents the last entry in our Pascal's row. And while we're at it, this one here, n1, that's going to equal n. So this is 12, always reflecting the power that we're expanding. So this is how we'll proceed. That is basically the binomial theorem. And if I wrote this, if we can write this in sigma notation, it's quite neat. We can say that the sum of, so more generally, rather than dealing now with a power of fixed power, a plus b to the power of n is going to equal, let's work this out, n0 is my first coefficient, a to the power of n. Our next coefficient is n1, a to the power of n minus 1, b. Okay, so a is coming down in power each time, and b is going up. So that this power plus this power always equals this here. And so we go on to write down all the terms, and the last one being nn, b to the power of n. Now this can be written in shortened format using sigma notation. If we go from r equals 0 to n, what are we saying? So it'll be n r, and it'll be a to the n minus r, b to the r. So that is our generalized term for a binomial expansion, and we're going to use that in our work as we proceed through and start to solve some problems using the binomial theorem. But that's the basis of what we go from. This is a really important sum here. It just represents the expansion of the binomial a plus b to the power of n. It covers the lot. So some work for us to do on this, which I believe is the last sort of section in chapter 1. So we'll spend a couple of days working through the problems on this. But that'll do for this one, and I'll see you in class.